So we've already had a look at our definition of what an acid is. It's a proton donor. We also are aware that when we get a bottle of an acid, that we're actually looking at an aqueous solution of it. It's that acid dissolved in water. So the best thing to look at its properties is to actually see what it really is. So to do the reaction of the acid with water and see what's actually present. It's by doing this that we can actually determine whether something's a strong acid or a weak acid. And here are some acids you've probably met before. HCl, hydrochloric acid, which is actually HCl gas bubbled into water. HNO3 or nitric acid, H2SO4 or sulfuric acid. And then we know that these react quite strongly. They were used in junior science because they react quite quickly. This is because they're strong acids. Weak acids, on the other hand, are things like CH3COOH, which is the active ingredient in vinegar. It's ethanoic or acetic acid. Citric acid you've probably met before, and you probably quite like the flavour that it has. Quite a sour flavour that makes your citric fruits have that sharp flavour. And tartaric acid is another thing that's found in a lot of fruits that makes them quite tart, hence the term. Okay, these ones have all got carbon in them somewhere, and so they're what we call organic acids. They also happen to be weak acids. There are others that aren't organic, but they're the best ones to show. So if you see something that's got a CH3 in it, it's a weak acid, because those hydrogens are not involved in dissociating, so breaking apart to make hydronium ions. It's the one on the end that is, or ones. Sometimes they've got more than one. So how do we tell strong and weak acids apart? Well, the first thing we can do is just by basic observations, and this is something we did in year 11 science probably. We looked at, for example, the reaction between 0.1 mole per litre of hydrochloric acid and 0.1 mole per litre of ethanoic acid with things like calcium carbonate, with things like magnesium. And while they had the same reaction, the ethanoic acid reacted a lot slower. Right, now if you did physical science, you probably also looked at things like conductivity. And what we find is that these ones conduct electricity poorer than these ones. Okay, and I'll give you a chance to have a look at that in class later, but we won't video it. So why is that happening? Well, then we go to another test and we check its pH. And we find that the pH of these acids at 0.1 moles per litre is about 1. Whereas the pH of these acids at 0.1 moles per litre is a lot higher. It's around 3, 4, sometimes even 5. Lemon juice has got a pH of around about 4. If it was too much lower than that, it would not taste very good, even on your fish. It would be too acidic, too strong for you. So if we were to keep the concentration the same, why is there such a difference in pH? That must mean there's a difference in concentration of the hydronium ion, because that's the important one. Okay, that's the one that determines pH using our calculations. So if I have 0.1 moles per litre of a strong acid, and it has a pH of 1, that means there's 0.1 moles per litre of the hydronium ion. That means that solution actually has no HNO3 left in it. It's completely reacted, hence the arrow, to become hydronium ions and its conjugate base, the nitrate ion. So it's completely dissociated. There is no HNO3 left in that bottle. It's all become these two ions. So if it's 0.1 moles per litre, then there's 0.1 moles per litre of hydronium ions, and if I do negative log base 10 of 0.1, I get 1.0. So that's why. It means there's a lot of these hydronium ions available to react with the carbonate ion to make CO2, or with the magnesium to make hydrogen gas in the magnesium ion. So that's why their rate of reaction is a lot higher. Conversely, weak acids you'll see have the equilibrium arrow. That's telling us that the forward and reverse reactions are both happening, which means it's not all turning into hydronium ions. What that means is I need to look at the pH and try to determine it. Now it's somewhere between 2.5 and 3. I'm going to be honest, I made up 2.7 because I know it's in that ballpark. It's about 2.7 to 3. I don't remember the number off the top of my head. Okay, it's not important. But I do know how to find out my hydronium ion concentration by going 10 to the power of negative 2.7 equals. So if I put that in the calculator, I get 2 times 10 to the negative 3 roughly. It's 1.995. So it's 2 times 10 to the negative 3. So that's much lower than the 0.1 moles per litre that I started with. In fact, it's about 100th of it. So it's about 100 times smaller. So there's actually very little hydronium. There's more hydronium than hydroxide because there's no hydroxide being made in this reaction. But it's only increased the hydronium ion concentration a little bit. Not completely like this one. This has shot it up by a long way. This one's only moved it up a bit. And so that's why it is acidic, but it's not as low as 1. Okay? What does that mean? Well, it means, I'm sorry I haven't written this up yet, it means that if I had a solution of this, most of the particles in there are actually that molecule. They're CH3COOH molecules. Only 2 times 10 to the negative 3 moles per litre of them are the conjugate base and the hydronium ions. So there's a much lower, even though these two have the same concentration, there's a much lower concentration of the important ion, hydronium, in this one, which means it's going to react a lot slower. Hydronium is present, so it still has a pH lower than 7. It still reacts with carbonate, it still reacts with metals, but it reacts much, much slower because there's fewer particles, so fewer successful collisions and so on. So looking at the other part of this topic, the reaction rate topic. So that's how these two things link. Weak acids bring everything from this topic together. Equilibrium, because you could draw an equilibrium expression for this. You have got rates of reaction because even though it's 0.1 moles per litre of acid, it's only 2 times 10 to the negative 3 moles per litre of the important ion for the reactions of acids. So it brings everything together. So I'm sorry, I'm just going to write something up quickly here because it's, I think, worthwhile. Okay, so I've just said there, in aqueous, so the AQ means dissolved in water, so it's a solution. In a solution of ethanoic acid, most of those molecules remain. They don't actually break apart, they don't dissociate is the word we use there. Only some become hydronium, lose the hydrogen to become hydronium, and become the conjugate base ethanoate. Okay? The words we use here is we say that strong acids completely dissociate. That's why it's an arrow, not an equilibrium. Completely dissociate. And these ones don't completely, so we say it's partially dissociate. And these words that I'm putting out are the reasons, along with some balanced equations would be good, that there are different rates of reactions for strong and weak acids.